All right, in our last video, we were talking about lab performance check solutions, also known as LPC. Great, yay, woo! I mean, I get real excited when I talk about this stuff, right? Okay, so anyway, we've been working ourselves through definitions and through this terminology that's used in a quality control lab. And this is one of them, again, that we have to ensure that we keep along for the ride because it's going to let us know is quality built into the batch of samples that we're processing and getting data for. So we keep referring back to this original EPA document. And again, the reason I'm doing it is because it is an environmental spin, but it's giving us some definitions that's also used in other areas or other facets of a laboratory field. And that's okay because some of these other organizations might not use every single one of these, but EPA does a pretty good job of embellishing kind of everything as far as quality goes and what is really a good SOP and a good method. All right, so we're moving on, and I told you that in this video, 3.8 and 3.9 are going to be our focus. So 3.8 says a laboratory fortified blank, whatever that means, or LFB, and a laboratory fortified sample matrix. So another fortification, whatever that means, but this time on the sample matrix instead of the blank. So LFB and LFM. Those are the abbreviations that we use on our samples when we begin to process them in a laboratory. So let's just read the definition, and then I'll take a few minutes and kind of maybe explain this in Tracy terms versus EPA terminology, being all prim and proper, right? So 3.8, lab fortified blank, LFB. It says an aliquot, okay, again, aliquot is just a fancy term for sample. A sample of reagent water or other blank matrix to which known quantities of the method analytes are added in the lab. So the method analytes are the things that you're looking for. So this seems like we're taking a blank and we're adding stuff to it. The LFB is analyzed exactly like a sample, and its purpose is to determine whether the methodology is in control and whether the laboratory is capable of making accurate and precise measurements, with accuracy being the most important piece here. All right, so that's an LFB. I'll explain that in just a minute. 3.9, the laboratory fortified sample matrix. So again, an aliquot, so a sample or a portion of an environmental sample to which known quantities of the method analytes, and again, that's the stuff that we're looking for, are added in the lab. The LFM is analyzed exactly like a sample, and its purpose is to determine whether the sample matrix contributes bias to the analytical results. The background concentrations of the analytes in the sample matrix must be determined in a separate aliquot, and the measured values in the LFM corrected for background concentrations. Woo! What a doozy. And again, imagine if you were a lab and you had to go through this method and be like, okay, how do we build an SOP around this? What is this really asking for? What is it referring to? What's the differences between these two things? I mean, they're both fortified, so we got to first start there. What does that mean? And then it's a blank as well as a sample matrix. All right. So let's Tracyfy this definitions, and let's talk about the differences here and what the role and the purpose of each one of these are. So we're going to start with fortification, because both of these use the term fortified or fortification in the definition or in the name. So fortification means you're going to add to it. That's what that is. All right. So we're not really necessarily talking about, adding something that's not supposed to be there, because in both of these definitions with fortification, it says you're going to add the analyte that you actually are interested in measuring. So I'm going to go back to our example that we keep using here, and that's iron in a cereal sample. So what this means is that this now is giving me time or a chance to take some solutions and add iron that I know in a certain amount into a sample. That's what we're after here, okay? So this is something that we're trying to measure in the procedure, And again, this is just an example. So what we're trying to find in a serial sample might be the iron concentration. I'm going to take a certain amount of iron and I'm going to add it to these solutions. But I'm doing it. This is something that I'm looking for, and it's something that I'm doing, and I should know what the result is going to be in doing this. Meaning, the first definition here is a laboratory fortified blank. So a blank, we've already talked about this. A blank could just simply be the solvent. Maybe that is just DI water, right? Maybe that's all that it is. Whatever the case is, use it. Acid, base. I mean, we talked about the options. So with the laboratory fortified blank, fortified means you add. And what do you add? You add what you're trying to measure. So in this solvent, what's going to happen is that I'm going to add the analyte that we are looking for. That way, this is a known concentration. I know what I've added. I know that it's there. And again, this should be different than the calibration concentrations that you have used to make your standards with. They should be totally different. So the SOP is going to explicitly lay out the step. Take this amount of this, add it to that, and dilute to the line. Ding, 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 ding. Shake, shake, shake. Mix and go run it. The reason for that is because the method requires it. If the method requires it, we have to follow it, so that way we don't invalidate the method. But it gives the laboratory a chance to make that judgment call on what they would like to use. So this is where the SOP comes in. It's slight modifications that we can change and customize depending on what our needs are. But that is a LFB. So the blank or the solvent, and I add a little bit of known stuff that I'm trying to measure into it. I know what that result should be, and I'll run it, and that is what should show up on the report. All right. So if I compare this to just the blank, right? The blank is just the solvent. That maybe is just DI water. Both of these get processed the same way. Both of these go through the sample preparation. Both of these go through the heating, the cooling, the processing, the filtration, whatever the case is. They all go through the same process. The blank doesn't have, maybe in this case, any iron in it at all. It is truly a blank. And I hope that I get 0 as a concentration maybe, because there should be nothing there at all. Okay. Then I'm going to take our blank, whatever we decided to use for our samples and that kind of thing, and I'm going to add in a little bit of analyte to it. And in this case, maybe a little portion of iron, a little bitty smidge of little iron gets sprinkled in. And then we go and run it. When we run those, well, we know again what the concentration should be. So this is a expected concentration that should show up on the report. And then I look at the report concentration, and I want to make sure, are these two things equal? I hope that they are. I hope that they get really, really close. All right. So what this is doing is that it is really kind of checking to make sure that the blank doesn't interfere with my sample reporting. That's what this is. All right. My blank, there is no interference at all. Because maybe, just maybe, there could be. You know, maybe there could be something in that solvent that's interacting with iron and not making it respond very well to the instrument or to the equipment or whatever the case is. Right? I don't know that. And one of the ways that I can prevent that or take that into account is if I run a blank that really shouldn't have anything in it at all, and then I run a blank with a little bit of what we're looking for in it, and hopefully it comes out and it matches what the expected value should be. If it does not match the expected value, maybe I messed up on sample prep. Maybe I need to do it again. Or maybe that solvent, whatever that solvent is interacting with the iron or the thing that I'm looking for, and maybe it's interfering with the reporting and interfering with the signal. So this helps me make that judgment call, and that's why the laboratory fortified blank is important. We also, again, want that concentration to be different than the calibration standards that we've made for our linear regression curve. We want these to be different. We don't want them to be the same. So preferably the SOPs will make you go down that rabbit hole of coming up with a concentration that doesn't quite match a standard. Okay? So that's the purpose of the LFB. We are making sure the blank does not interfere, aka the solvent interfere with the sample analysis. Okay? So there's LFB at its heart. That's why we use it, and that's why we do it. Now, there's another fortification sample here, and this one was the laboratory fortified matrix, LFM. So M is the term for matrix, and matrix means, I'm going to put in parentheses here, everything. Keep that in mind. So it's not just the solvent. It's not just the water. It's not just the acid or the base or whatever you put in. It's really the entire matrix as a whole. So, that means we understand that a lot of times the samples are bringing to the picture all of the other things that we don't want to look at, that we don't want to report, but they're there along for the ride. And we just want to make sure that, okay, that's okay as long as you don't get in the way. That's okay as long as you don't interfere with the signal of what we're actually trying to look for. So, imagine this like going to the doctor's office, and you walk into the doctor's office and the appointment's for you, but you've got a family of 10. So you go into the clinic room with your family of 10, and the doctor comes in and they make a diagnosis. If the family of 10 begins to get involved in the situation and make things worse, then that family of 10 is going to get kicked out. That's not going to be allowed, right? There's a problem when we have to be able to fix it. We don't want the analyte to bring a family to the picture that's going to get themselves involved in the analysis portion of the samples and the standards and the reporting. And that family is called the matrix, okay? So, laboratory fortified matrix. It is the same as the LFB, except this involves the matrix portion of the samples, not just the solvents, or aka the blanks. All right. So the process is the exact same. What happens here is that we have a known amount that we are using, and this is of our analyte that we want to look for. So in our example that we've been carrying through all of these, it's been a known amount of maybe iron, right? So again, I'm taking the sample, I'm adding a known amount of iron to it, and I know what should be there, and I know what should not interfere, and I know what my report should be like, and hopefully on the back end of this, it actually shows up that way. So it says an aliquot of an environmental sample to which known quantities of the method analytes are added to the lab. So what happens here is that, let's say I go out to the river and I get a sample of water, and I bring that sample of water in, and I run the sample as it is. All right, so I run my sample, and I get a report. So my sample is going to say, okay, based on your calibration curve and the instrument response, your sample has a concentration of 5 ppm. Again, whatever that means, right? Parts per million. Okay, then what would happen is that prior to running it, I have taken a portion of that sample and I've put it into a different, maybe volumetric flask or some type of container. And I have added a known amount of iron into it. Okay, I know what the concentration of that is. I know how much I've added. I know what my signal response should be. So based maybe on a little bit of math, and we're not going to go into that right here, we're just defining definitions. What would happen is that I would make the decision, okay, based on the iron amount that I've added, my signal should go up by another 2 part per million maybe, right? That's really up to the directions. It's up to the SOP. It's up to the company to determine how much of an increase they want to see here. But this is a lab fortified matrix. So my sample's been ran. My sample has a number, and my original sample that's not really been modified has a 5 part per million concentration of maybe iron. So I'm going to run it again. There's another sample in the batch that has a spike, aka that's kind of what this is called, of iron into the sample. And based on that amount that I've added, I expect that my signal should go up by a factor of 2. So this one's going to get analyzed. And when I get analyzed, my expected value here that should show up on the report would be a 7 part per million now instead of a 5 part per million, because I know that I've added to it. My signal should go up, my concentration should go up, and I know how much I've added, so I know how much it should go up by. That is a laboratory fortified matrix. That's what that is all about. All right. So in the directions, that's kind of what it tells you here. An aliquot of an environmental sample to which a known quantity of the analytes added. It's treated just like a sample. And we are double checking to make sure now that the matrix does not interfere. There could be other things, again, the family that's coming along for the ride, and we don't want them to interfere in anything. We want them to be quiet. We want them to be still. We don't want them to stir up any drama. And the same thing happens here in the lab. And this is to help make sure that that does not happen. It says that the background concentration of the analytes in the matrix must be determined in a separate aliquot, and the measured values in the LFM are corrected for those concentrations. In other words, that's kind of what we're talking about here, right? We want to make sure the matrix is not affecting the values. We want to make sure that we have a base number to go off of, and then we want to make sure that when we add it, that we don't see anything weird or wonky with the value. In other words, if I add this known concentration to my lab fortified matrix, then my expected concentration here, if that's a 5 still after that, I know that something's wrong because it started out to be a 5, right? Maybe it started out to be a 5, but this is now not changing. That doesn't make any sense. If I add more, my signal should go up. And hopefully that shows up on the back end of this. All right, so a lot of people use a term here, and this term is called a spike. I am spiking the sample in order to see what my end results are going to be. Now, some people, some labs, some methods might define spike as something different, but very often they regard this process the same way. So again, the definition is taking a sample, adding something to it, and hopefully that result goes up because you've added to it. And it's always adding the thing that you're looking for. So laboratory fortified blank and laboratory fortified matrix. Fortification means you are adding something. What are you adding? You are adding the thing that you're looking for, and we're adding it to the blanks to make sure they are not interfering with the results. And we're adding it to the matrix, or AKA the sample, to make sure that that is not interfering with the results either. Both of these results should go up from the blank run only and from the sample run only, or the matrix run only. All right. So that will finish up lab fortified blank LFB and lab fortified matrix LFM. So in the next video, we might finish up the definitions, and in the next video, we're going to continue on, and we're going to go into 310, and we're going to go into 311, something called a stock standard solution and a primary dilution standard. That's where we're going to start dancing around and talk about what those definitions are. What are they? What are their purposes? How do they play a role in quality? Because that's what this course is all about. And that's why we're dissecting the method here, because all of this plays a direct tie into quality of data that comes from a laboratory result or procedure or process that they are doing on a daily basis.